Hello everyone, and welcome to MSCI 718 Lesson 3, Stats Review 2. By the end of this lecture, you'll be able to calculate standard error and confidence intervals, interpret confidence intervals, define levels of significance, power, and type 1 and 2 errors, and interpret measurements of effect size and argue for providing practical significance. And as a heads up, this might be the most important lecture in this class, because confidence intervals are one of your best tools for analyzing and communicating estimates, and the difference between statistical significance and practical significance is, well, significant. So you want to pay special attention to these concepts. Let's start by diving into standard error. Previously, we talked about variance. We can capture the variance by calculating the sums of squared errors, and then we can calculate variance based off of that. And this can be hard to interpret, so we can calculate standard deviation. So square root of the variance, we arrive at the standard deviation, which gives us a sense of how the data varies, especially around the model of the mean. For example, with our statistics professor and their number of friends. So the standard deviation shows how well the mean represents data. You might have a very good fit of the mean to the data, or you might have a less, like a poorer fit of the mean to the data with larger standard deviation. And the mean is this simple statistical model that can be fitted to the data. It represents how well it models the data, and this is true in statistics generally. Outcome I equals the model plus some epsilon or error I. So each observation is the model plus some deviance. However, the standard deviation really only tells us about the sample we looked at. For example, the statistics professors we asked had a mean of 2.6 friends, standard deviation 1.14. But usually we want to infer something about a target population. For example, statistics professors in general have a mean of 2.6 friends. How do we do this? Well, let's take a look at the population. If you take one sample, you might have a value of the mean of 9. So the value of the mean for that sample is 9. You take another sample, you might have a mean of 10. Do it again, you get the mean of 10, then maybe 11. You can keep doing this with any number of samples. So the mean also has a distribution. Can we figure it out? Because if we can understand how our sample might model the mean of the population. Let's start by trying to tackle variance. Let's say you have one sample and it's an independent, identically distributed sample. So you've got x1 through n. They're normally distributed around a mean of mu and a variance of sigma squared. The total is the sum of the elements. So we calculate the sum of those different elements. And since the samples are independent, they don't have a covariance, the variance of the total is the sum of the variance, which means we take the variance of the total, the variance of the sum of those items, which is the sum of the variance of those items, which is all the same because all of them are distributed with a variance of sigma squared, which means we end up with n sigma squared. So this is for the total value of our sample. The mean is the total divided by the number of samples. So x bar is t over n. So we can use the total to calculate the variance of the mean. We take the variance of x bar, which is the variance of t over n, which corresponds to the variance of t over n squared. We then plug in the variance of t, n sigma squared over n squared, so it's sigma squared over n. And since we don't know the population variance, we use our estimate, the standard deviation of the sample, which is usually denoted as S. So we now have an estimate for the variance or the standard deviation. So the standard deviation of x bar, or of the mean, is the standard deviation divided by the square root of n. And it's known as standard error. So if we go back to our population, we now have a bit of an idea of the distribution. This is the sampling distribution. It's how the means will change if you take lots of different samples. We take the mean, that's our estimate. We have the mean of the sample. It's the same as the mean of the population and the mean of the means, as best we can calculate from a single sample. And we have the sampling variation. So it's known as standard error. And in this case, standard deviation is the standard error of the mean, which we've calculated to be s over square root of n. So now it's your turn. Individually, using whatever tools you want, calculate the standard deviation and the standard error of these numbers. Submit online using the instructions. I'll wait. Go.